We are going to look at hypothesis testing for discrete distributions. And I would recommend you to start with the article at this link. You can search it by its name and author to get a better understanding of the importance of this concept and how is it applied in a day-by-day life. On the next pages, I'm going to take some examples. Please pause the movie and read this question. I created an Excel simulation to see how this distribution looked like, a binomial distribution. So X is binomially distributed with 15 and probability of success 0.2. This is under H0. So under H0, I want to see the shape of the distribution. So here is my simulation. I put in my Excel spreadsheet P, which is 0.2, a value for n, so that later I can change them. N is 15, and all possible values of x are from 0 to 15. You can see how I use the Excel spreadsheet as well. And Excel can calculate for me directly the probabilities. So there is a function, binom distribution, with parameters x, n, and p exactly in that order. And also wants another parameter, and I type false. False means the probability distribution function is calculated and not the cumulative one. I drag the formula down, but I have an error. I left it on purpose. So, as you see, when I drag the formula down, the numbers are dragged accordingly. So I need to put a $sign because I want to keep n and p constant in all my formulae and just the x changes. So now when I drag it down, I have the probabilities. I check that they add up to 1 quickly. It's a way of checking that I'm correct. Not a guarantee, right? So all the probabilities add up to 1. And now I want to see the graph. So I choose insert a bar graph. And this is how the binomial distribution looks for n equals 15 and p equals 0.2. Now, my first question asks, what is the significance level of the test? Let's stop a bit and think. Can you pause the movie and read the next question? In the case of this problem, the critical region is given. So I am told that the critical region is 0 and 1, meaning that if the x value is 0 or 1, I'll reject the null hypothesis. So this is a better diagram. If x equals 0 or 1, I reject the null hypothesis. If it's 2 or more, I accept the null hypothesis. Therefore, the probability of a type 1 error will be given by the probability of x being 0 plus probability of x being 1. And this is what we calculate in this movie. Well, instead of calculating it, I copy it from another Excel cell where I calculated before. So adding these two probabilities, of course, you'll use your calculator, gives me the probability of a type 1 error. Now the probability of a type 1 error, C, is 16.7%. In this case, probability of a type 1 error is the same as the significance level of the test. We will see later that not always in the case of discrete distribution, the two are equal. Let's now look at the third question. So we are asked to test H0, P equals 0.2 against H1, P equals 0.1. So probability of a type 2 error, we know, and we always write this, we always scaffold our thinking. Probability of accepting H0, given that H0 is false. So When do we accept H0? If we look at the decision rule, we accept H0 when x is bigger or equal than 2. Given that H0 is false, what does it mean H0 is false? Means H1 is true, so the real probability is 0.1. Therefore, my x is binomially distributed with 15, and instead of 0.2, we have 0.1. So I need to find this probability on the new distribution. 1 minus probability of x equals 0 plus probability of x being 1. And don't forget that we are on this distribution. And I get 0.451 to 3 significant figures. So this is a probability of a type 2 error in the case when p is 0.1. Please pause the movie and try this question. It is very similar to the previous one. It's just another discrete distribution. It's a Poisson distribution this time. In order to understand this question better, I plotted the graph of the probabilities for a Poisson distribution with a mean of 6. And here I have probability of x being 0, 1, 2, and so on to manipulate easier with numbers. When I add up all probabilities, I get almost 1, but not quite, because remember that the domain for the probability for the Poisson distribution is 0, 1, 2, 3, up to infinity. So x can be anything. However, the probabilities get smaller and smaller. I am now asked to conduct a hypothesis testing of H0, lambda equals 6, against H1, lambda smaller than 6, at 2% significance level. So I'm giving the significance level of the test. That's called nominal. It's what they nominate, what they tell me. So the nominal significance level. This concept was not for the continuous distributions, because all the time for the continuous, nominal is equal to actual. Let's look what it means. If they ask me 2%, I need to look on the left-hand side, here or here, where are 2%? What probabilities add up to 2%? So if I start adding on this diagram, I think it's better if I add another column with a cumulative. And here we go. We look at 2% significance level, and we see that 2% are up to here. So probability of x being 0 and 1. When we reach probability of x equals 2, we have already 6.2%. So these two 0 and 1 add up to 1.74%, and probability of x being 0, 1, 2 together add up to already 6.2%, as you see from the column, give me probability of x smaller or equal than x, cumulative. This means that the critical region is x is 0 and x equals 1. That's where I reject H0. And the actual significance level of the test is 1.735. 1.735% or 1.74% to three significant figures. State the probability that a type 1 error occurs. The probability of a type 1 error occurs is, if you remember the definition, probability of a type 1 is probability of reject H0 given that H0 is true. So I'm under H0 is true if I'm under this distribution, and I reject it for 0 and 1. So probability of a type 1 is actually the same as the actual significance level of the test, is 1.74%. And for the last question, given that lambda is 3, so I need to find the probability of a type 2 error. And the probability of a type 2 error is probability of accepting A0, given that your distribution is Poisson, not of 6, but of 3. Where do we accept H0? Probability of x bigger or equal than 2, given that x is distributed Poisson with 3. And probably I'll do 1 minus probability of x equals 0 plus probability of x equals 1, or any other means you have to calculate it, but don't forget that you are on this distribution. My answer is 80.1% for a probability of a type 2 error. Let us look at this example where we actually carry out an hypothesis testing from the beginning to the end. Okay, so I'm bringing in the graph of the distribution. This is a probability distribution function, and the one with the dotted line is accumulative. And these are the values. That's a possible values of x, and they continue up to infinity. These are probabilities, probability of x being x, and this is accumulative. So we want a 5% significance level to the right. So we look to the right, which of the numbers add up to 5, the probabilities add up to 5%. Therefore, if we want 5% to the right, we want 95% to the left. So our border for the critical region will be between 2 and 3. Therefore, in this area, we will reject H0, and here we will accept H0. So the critical region will consist of values x bigger or equal than 3. Calculate the probability that a type 1 error occurs. Probability of a type 1 is probability of rejecting H0 given that H0 is true. So given that you are on the distribution drawn here, so it's probability of x bigger or equal than 3, given that your x is Poisson of 0.8. So it's the sum of all these numbers, actually these numbers from here. So it's going to be 1 minus 0.953, which gives me 0.047. So your probability of a type 1 is 4.7%. Let us now look at question B, where it states that now the test is carried out and the observed value is 3. The observed value is 3, so 3 is odd, it's in a rejection region. Therefore, the conclusion of my test is that I reject H0. Therefore, the mean of the distribution is bigger than 0.8. At 4.5% significance level. No, at 5% significance level. Sorry, at 5% significance level, the mean of the distribution is bigger than 0.8. So just to point out, see in this case how the significance level is 5%, and the probability of a type 1 is 4.7%. That can happen in the case of discrete distributions. State which type of error in the hypothesis test, type 1 or type 2, could have been made in these circumstances. Since the conclusion of the test is to reject H0, then you could have made the probability of a type 1 error. That was an example of a hypothesis testing with a discrete distribution when a single observation is made. We carry out in exactly the same way hypothesis testing with a single observation for both Poisson and binomial distributions. We will see later how we carry out hypothesis testing for population proportion, when in the case of a binomial distribution, we look at a sample and the proportion of a sample.